So yesterday we started to talk about ammonia combustion, but we ran out of time, so we got through the blow-off portion of the talk, and so the rest of the ammonia material that I want to cover today involves pressure effects on turbulent burning rate, and then second of all, on how it influences emissions production, especially NOx and nitrous oxide, N2O. So let's first talk about the pressure effects on turbulent premixed lean ammonia hydrogen flames. And this is work that we did in collaboration, again, with our colleagues Andrea Gruber at SINTEF in Norway, and M.K. Lee, who was a postdoc of mine, and now at University of Houston, did some of the spectral analysis, and Foreman was involved in this work. And my postdoc at the time, Martin Reith, who's now a staff member at Sandia, led this work. So just to remind you from yesterday's talk, we mentioned that gas turbines operate at pretty high pressures, 20 to 30 atmospheres, although a lot of the lab experiments that we're conducting today are still done at much lower ambient pressures or slightly elevated pressures. And because of this, it's not altogether clear what pressurized conditions, how it affects the turbulent flame propagation and emissions formations. And up until now, computations, when you go up to high pressure, flames become much thinner, and the turbulence dynamic range of scales goes up because the small scales, the chromatograph scales, get smaller as well. So all of these imply lots and lots of resolution requirements and computational costs. So it's been kind of restrictive up until recently. There's been some normalized turbulent burning velocity experiments. Kobayashi and Venkateswaran have done some nice work in trying to measure turbulent burning velocities as a function of pressure. And as I said yesterday, ammonia is a very promising energy carrier for zero carbon combustion. And we can, compare trading off the problems with the hydrogen storage and transport. Ammonia might be a nice way to provide dispatchable energy and even convert it back to hydrogen where you need it. So also we heard yesterday that in the blow-off talk that you could take blends of ammonia, hydrogen, nitrogen, and optimize them to have unstrained laminar flame properties that can mimic what we currently burn in gas turbines with natural gas. So at least at the laminar level, laminar flame speeds, adiabatic flame temperatures, thicknesses, and so on, we can tailor the mixture by adding less or more ammonia or hydrogen, nitrogen to that mix to get reproduce, try to mimic these properties. However, lean turbulent combustion behavior of these ammonia, hydrogen, nitrogen mixtures we saw yesterday also differs a lot when you add turbulent stretch to these flames, because of, especially due to the curvature stretch that induces, that amplifies the thermodiffusive intrinsic instabilities and locally enriches with the flame in these positive cusps that are convex towards the reactants with hydrogen, which then accelerates combustion in those regions, not only by generating more flame area, but also by vastly increasing the burning rate per unit surface area. And so this effect is not fully understood yet, especially at elevated pressures. So what we did was to conduct a series of DNS simulations. These are lean premixed ammonia, hydrogen, nitrogen flames at a 40 to 45 to 15% volume ratio for ammonia, hydrogen, and nitrogen. And the overall equivalence ratio is 0.45, very lean. And we ran two cases, one at 1 ATM and the second one at 10 ATM. The reactants were preheated to 750 Kelvin, and the flames reside nominally in the Borgy diagram for premixed combustion in the broken reaction zones regime, where the Karlovitz number is quite high, 600, and we pushed the turbulent Reynolds number as high as we could for DNS purposes, and this was a little bit over 1,000. The simulations between the 1 and 10 ATM case were designed on purpose to have normalized parameters, controlling parameters like the turbulent Reynolds number, the Karlovitz number, and the Domkohler number, which are consistent between 1 and 10 ATM. This was not a cheap calculation. It was run with the S3D DNS code. It ended up costing or requiring 11 billion grid cells on the final mesh so that we could resolve these very, very thin flame fronts. We adopted a 19-species chemical mechanism, just as we used in the blow-off study yesterday, developed by Zhang et al. At UC San Diego. And as I said, we ran DNS with the S3D Legion code on, at that time, it was the petaflop Summit Supercomputing Center on about 1,000 compute nodes. These are GPU compute nodes, so I think those were NVIDIA ones, using a large insight allocation from DOE. And so this picture on the upper right just shows the simulation setup. We have a horizontal laminar flame, this lean ammonia, hydrogen, nitrogen air flame, horizontal. And then it's a temporal shear layer, so it evolves in time rather than in space. And we have reactants on the top and products on the bottom. And then we allow a shear layer to develop ahead of time until it transitions into shear-driven turbulence, and then it's allowed to interact with this flame. Just to show you on a Borgy diagram of the normalized RMS velocity plotted versus the integral length scale, both normalized by laminar flame quantities, the laminar flame speed and the thick nominal flame thickness. You can see at 1 ATM on the left and 10 on the right that the temporal evolution, as shown by the colored symbols, going from dark red to yellow from normalized times from 100 to 350, these flames have a similar trajectory. And this was by design when we set up the non-dimensional turbulent Reynolds number, Karlovitz, and Domkohler number. So ideally, you would think that the flames should behave in a similar manner at 1 and 10 ATM. Now, in physical experiments, it's very hard to do this sort of thing because usually they don't, they have the same burner, same diameter, and so the Reynolds number actually changes with pressure, which is not unless you had a series of different diameter burners that you could control and do like we're doing here with DNS. So before I show you the movie of the evolution of these flames at ambient and elevated pressure, I want to show you just a slice in the span-wise direction of the shear layer of the heat release rate at 1 and 10 ATM. In the top figure is the ambient pressure flame, and in the bottom is the 10 ATM flame. And I just want to call your attention to just a piece of this. Well, first of all, I want to say that on top of the isocontour lines of the heat release rate, where red is obviously high, and this is on a log scale, so it's actually the log of the heat release rate. I've also drawn some iso lines that show you where the flame brush is. And so 800 Kelvin is white iso line, which is the front of in the preheat zone of the flames. And 1,000 Kelvin is in gray, and 1,500 Kelvin in black towards the product side of the flame brush. And so you can see visually very clearly that there are very large differences in how these flames burn at 1 and 10 ATM. I think I mentioned this yesterday as motivation for looking at some of the hydrogen flames. But basically, just to reiterate, what you see is that there's a significant broadening of the preheat layer for the 1 ATM flame. And that doesn't exist at 10 ATM. So the flame is, and that suggests that turbulent diffusion is much stronger relative to molecular diffusion of either ammonia or hydrogen at 1 ATM, but that the molecular diffusion at 10 ATM is, and the local enrichment in these positive cusps towards the convex side overwhelm turbulent diffusion. And so the flames burn more or less like a flamelet at higher pressures, where the isolines across the flame brush are more or less parallel to one another. You can also see that the burning rate, as measured by the heat release rate, is much more intense. There's darker red, much more prevalent darker red regions where the heat release is superadiabatic due to this local enrichment, faster combustion rate, due to the amount of hydrogen that's locally finds its way into these positive cusps due to curvature stretch. So let me play the movie of the temperature so you can see what overall what the 3D field looks like. And on the right, I will also show plots of the flame surface density. So that's the amount of area that's generated at 1 and 10 ATM. 1 is black line, blue is the ammonia hydrogen, or 10 ATM. Blue is 10 ATM, black is 1 ATM. The dashed lines for the stretch factor, which is the normalized consumption speed, normalized by the area. The dashed line is for hydrogen component, and the solid lines are for the ammonia component. Blue, again, is 10, and black is 1 ATM. So you'll see the evolution of this as it develops. I should say I flipped this on you, so now the products are on the bottom and the reactants are on the top. Flame is horizontal and the shear layer is forming. So if you can see, we see a much faster increase in the flame surface density. We see an increase in the fuel consumption rate and also in the stretch factor, which is a measure of the burning intensity. We see that certain regions at 10 ATM on the right image have very super equilibrium, superadiabatic temperatures. Also, I'm not showing this here, but the radical pool, OH, hydroxyl radical is also at superadiabatic conditions. And locally, there's a lot of enrichment with hydrogen above the global equivalence ratio. So another feature of these high pressure flames is, as we measure by the magnitude of the gradient of progress variable, is that the flames become thinner at higher pressure. And what that means is that you have steeper gradients across which that amplify the molecular diffusion, the diffusion rates of hydrogen locally there, and the thermodiffusive effect. So this is just a comparison of the species diffusion terms for hydrogen normalized by their minimum and max values for 1 ATM and 10 ATM on the right. And you can see that the hydrogen diffusion rates are much more amplified compared to the laminar flame at 10 ATM on the right compared to 1 ATM on the left, which is a clear indicator that we have enhanced thermodiffusive instabilities. And therefore, that kind of explains the degree of superadiabaticity that we see. And this little cartoon image on the bottom kind of says what I said yesterday. In these positive cuts, you have preferential diffusion of hydrogen there compared to defocusing of heat, where hydrogen here is the deficient reactant at these lean conditions. And so what that does is in those regions, it enhances the amount of hydrogen present. The equivalence ratio goes up, as does the temperature and radical pool. This is just a still image of that diffusive flux of hydrogen at 1 and 10 ATM. On the right here, then, is the conditional heat release rate at 1 and 10 ATM, doubly conditioned, first on temperature on the abscissa, but then the color-coded lines, the red and blue lines, correspond to different quartiles of curvature, red being positive curvatures that are convex towards the reactant stream, and blue being concave curvatures that are in the opposite direction. And it's interesting to see, first of all, that flames at 10 ATM respond more strongly to preferential diffusion, and they're more equivalence ratio sensitive, such that the heat release rate in those positive quartiles, the red lines, are substantially higher than those in the concave regions. And comparatively, at 1 ATM, the 10 ATM heat release rate is also much higher. Just to give you even further evidence of this, we can, and this is the beauty of DNS, you have all of the species, scalars, temperature, everything. So what we're doing here is showing the several other quantities through a 1D cut of that 3D shear layer that I just showed you. So you've already seen the temperature field, which is the top left ones, and then the top two left ones, and then below that is the hydrogen the equivalence ratio in the bottom left two plots at 1 ATM on the left, 10 ATM on the right, and you can see there's considerable enrichment at 10 ATM to values, the red and the yellow colors, which are above 0.45. They go up as high as over 0.6 locally. So 20, 30% enrichment locally just due to stretch effects. If we look at the top right plot, which is showing the OH radical, you can see there's considerably higher amounts of OH at 10 ATM. And don't be fooled, the dynamic range of color scales are different between 1 and 10 ATM. So the 1 ATM only goes up to 1.6, whereas the 10 ATM OH contours go up to 8. So those red colors and yellow colors for the high pressure flame are substantially higher than they are at 1 ATM due to this local enrichment of hydrogen. And then lastly, you can see the magnitude of the gradient of the progress variable, which is an indicator of the thickness of the flame, and also used to measure things like the scalar dissipation rate of progress variable if you square it and weight it by the diffusivity. And you can see there's much higher mixing rates upstream in the preheat zone, where the flame has accelerated and propagated to consume more reactants at 10 ATM. Another way to look at this is to take a RANS average across the shear layer. And so again, at 1 and 10 ATM, left and right, I'm plotting the RANS average of the velocity, normalized velocity fluctuations, velocity field, normalized by the laminar burning velocity, respectively, for each pressure. And then on top of that, the three colored lines are progress variable at 0.2, 0.5, and 0.8, going from white to yellow to black, is going from the front of the flame brush to the product side of the flame brush. And you can see very clearly that as we simulate in time, because this is a temporal shear layer going from left to right, that the 10 ATM flame brush is accelerating downwards. It has this bend as it's going faster and faster and faster relative to the development of the shear layer. As before, then that results in, in increased flame surface area generation, as shown on the right. So in this section, then, we performed DNS of these lean ammonia, hydrogen, nitrogen inner flames at different pressures in shear turbulence. And despite the flames normally having parameters that would allow them to have the same turbulence-flame interaction, both flames behave very, very differently. And just to reiterate, the 1 ATM flame exhibits significant preheat zone broadening due to turbulent diffusion. You can probably neglect, to some extent, molecular diffusion, and a strongly disrupted flame surface. 10 ATM flame features very strong cellular structure, strong superadiabaticity, faster flame surface area growth, faster fuel consumption, and thinner flames despite the high Karlovitz number. It's very, very robust. So now, what effect does all of this have on emissions generation? So let me now switch gears a little bit and talk about NO and N2O emissions. This is, again, collaboration with Martin Reith, Andrea Gruber, and this first study with emissions is where we varied we used the same lean DNS conditions at 1 in 10 atmospheres to look at pressure effects on NO and N2O generation. But we also ran some cases at different equivalence ratios. So we ran cases at 0.9 and 1.1 equivalence ratio in addition to the pressurized cases. And the same conditions as before for the previous case as far as the preheat temperature and composition of the fuel. I should say that the cases at 1 ATM at different equivalence ratios were run in a planar jet as opposed to a mixing layer for the pressure comparison, but other than that, they're quite similar. So I'll just give you the punchline on what happens. What I'm showing here is the volume integrated NO and N2O net production rates per unit heat released, and also the normalized volume integrated heat release rate for the 1 ATM and the 10 ATM lean, the lean ammonia hydrogen nitrogen air flame plotted versus time. And so what you can see here, let's see, the N2O, first of all, is the blue line. The solid black line is the bold solid black line. It corresponds to NO. And then on the right ordinate, I'm just showing the heat release rate in the grayish colored line. And what you can see is that for the lean case at 0.45 equivalence ratio, the higher pressure flame is much more unstable, accelerates faster, like we just talked about, compared to the 1 ATM flame. But interestingly, at 10 ATM, the net NO production rate is much reduced compared to the 1 ATM case. And it approaches a steady value that's significantly below that observed at 1 ATM. And you can see that in the black solid lines between the upper and bottom plots. So in fact, we get about an 8-fold reduction in NO production. And however, the opposite is true for N2O. The blue lines, comparing those, we actually see still quite a bit of production that's elevated at high pressure. So the good news is NO is reduced, but N2O still stays elevated at high pressure. We can also look at the effect of the local topology changes in the turbulent flame on the instantaneous NO and N2O. So NO is this, well, I should say on top of these isocontours of NO and N2O are again, the isotherms corresponding to 800, 1000, and Kelvin, and to the temperature at which heat release is maximum at the laminar flame, which is the black line, just to show you where the flame brush is relative to the NO production. And, and so we can see that overall, as I showed in the last slide, the 10 ATM case features much lower NO mass fractions compared to the 1 ATM case, so the top and bottom row comparison on the left panel. And the reason for this is largely because of the decrease in the radical pool that's formed. So H atom, O and OH, due to chain termination, 3-body reactions, H plus O2 plus M, forming HO2, which is much higher, increased collisions as you go up in pressure. And so because you don't have those radicals, you don't, like H atom and O atom, you don't form as much NO at high pressure. However, the local NO mass fractions still can significantly exceed the laminar peak values at these turbulent conditions. And you can see some focusing at 10 ATM, again, on the positive cusps where you see thermal NO focusing heat and radicals like O atom to produce higher levels of thermal NO there. The NO and N2O mass fractions in these positively curved flame elements are for both N2 and NO are more pronounced. And the reason that we don't see N2O decrease at high pressure is largely due, again, to the lack of H atom due to three-body collisions and increased recombination at high pressure, which produces less H atom. And you need H atom, which in the main consumption reaction for N2O, R61, shown here, that converts N2O to OH and nitrogen. But because you don't have enough H, you don't convert over to nitrogen as much as you do at lower pressures. We looked at the pathways for NO and tried to do an equivalence ratio comparison between the lean 0.45, 0.9, and stoichiometric flames. We find in this plot on the left, I'm showing the comparison of the three flames, 0.45, 0.9, and 1.1, turbulent flame compared to its own laminar flame, where the very leanest case is in black and gray, the 0.9 is in blue, and the 1.1 equivalence ratio flame is in red and orange. And so you can see in the parentheses whether it decreases or increases relative to the laminar flame NO. And I've denoted here the different pathways that are in play here: the thermal mechanism, the DeNOx mechanism, the HNO mechanism, which is important for fuel-bound nitrogen, like ammonia reactions, and then lump together all the other mechanisms. So the punchline is that the thermal pathway is relatively insignificant at very lean cases, but it becomes more important as you move to richer cases at 0.9 and 1.1. The DeNOx pathway shown in this plot is responsible mainly for the consumption of NO. So for the leaner cases, NO consumption goes down, while it goes up during the turbulence-chemistry interaction for the richer case. The HNO pathway to NO production is large. You can see for the very lean cases compared to 0.9 and 1.1 equivalence ratios. And it's only marginally affected by turbulence-chemistry interactions. That pathway is really fast. So it can withstand very, very high mixing rates and still progress. If we compare pressures on the different pathways, again here, the black and gray lines correspond to 1 ATM. Again, this is equivalence ratio of 0.45 only. So 1 ATM for the turbulent case in gray, black is the laminar corresponding case, and 10 ATM in the dark blue and light blue are the turbulent and laminar cases for elevated pressure. So if we compare the 1 bar and 10 bar case, we suggest that the importance of the thermal pathway goes up with increased pressure, but it's weakened under turbulent conditions. So the thermal pathway is responsive to turbulence chemistry interactions, and so it likes to have moderate levels of mixing, but if you mix too much, too fast, it doesn't form. On the other hand, a decrease in NO consumption, we see a decrease in NO consumption through the DeNOx mechanism, and a decrease in NO production through the HNO pathway, and a slight increase in NO production through other pathways. And the net result of all of this is that we see lower NO emissions at 10 bar compared to atmospheric pressure conditions, almost an order of magnitude lower. Another interesting way to look at these kinds of emissions quantities is to look at the nitrogen flux through the system. And on the left is a flux diagram for N2O, on the right for NO. And then, again, in parentheses, we're comparing the turbulent flux with the laminar flux through the corresponding unstrained laminar flame. And we can see a clear difference is observed for the nitrogen flux at the time of maximum generation of N2O, while the formation of N2O from NO and NH in the left diagram is only slightly increased at 10 bar, but the formation of nitrogen via N2O is cut in half compared to the laminar case, as I already showed in the before, and that's because we don't have H atom that's being used in three-body recombination reactions. So the largest, okay, so basically you're not completing your reaction to form N2 because of the unavailability of radicals at high pressure. We went on then to try to simulate an axially staged lab scale burner that was developed in Norway at NTNU. And following on the work of Kobayashi and others, where they find that the NO is minimized at slightly fuel-rich conditions, 1.1 to 1.3. The thought was that you might be able to minimize your emissions through a rich quench lean staged burner configuration. And so there's many groups right now working on this, both experimentally and as well as computationally. So this is just one of the designs. And so it shows that the primary, this is actually a picture of just the secondary stage, but the basic idea is you burn slightly fuel-rich, 1.1 to 1.3 in the primary combustor, and then you end up with hot product gases and at equilibrium conditions at the exit of the primary combustor and leftover hydrogen for these slightly rich conditions. So hot vitiated products containing hydrogen, water, and other stuff. And the idea is to have additional injection of dilution air in the second stage that would then mix with this vitiated product stream from the first stage, and would burn mostly as a hydrogen, diluted hydrogen, inverted diffusion flame. You think about it, you've got air coming in as like in a transverse jet in crossflow, and the transverse stream is the hot fuel and cold air. So it's kind of an interesting configuration. And the design considerations then are what kind of air split ratio you want to have between the primary and the secondary combustion stages. And then also people are worrying about incomplete consumption of ammonia from the primary stage. So there may be a few % of ammonia slip near the walls, which are colder, that gets into the mixes with the equilibrium products or gets into the second stage and can create or generate additional NO through the nitrous oxide pathway. So those are some of the issues. So this is just a bluff body configuration where we have the main air fuel injection here, and then secondary air fuel injection, if they do fuel. Sometimes it's just dilution air coming downstream in this picture. What we tried to do is to simulate this with DNS. And here we're using the adaptive mesh refinement code, Paley-LMX, which is the LOMOC code that allows us to put the grid where the flame zones are and where the high temperature regions are, where the high gradient regions are. And so the right image here just shows the computational domain where we have a turbulent inflow of reactants, and then we have no-slip walls. The length of this is about 147 millimeters long, and I think it's about 80 millimeters wide. This was all done at 1 ATM, the experiments and the DNS. And the inlet bulk velocity is pretty low. It's 15 meters a second. So the Reynolds number, based on this bulk speed and diameter, was about 10,000. The Kolmogorov scale, our smallest turbulence scales, are roughly about 45 microns. And the equivalence ratio here, we went slightly rich with 1.15. And again, we use the Young mechanism. So our initial comparison of the DNS and experiment, shown here in terms of the RAND's average streamwise velocity in the images on the left, show the DNS on the far left in the experiment. And then we took a couple of axial cuts, showing the radial profiles between the experiment and computation on the right for the reacting case. And we get reasonably good agreement in the streamwise velocity for the reacting flow field. The DNS are the red dots, and the experiments are the the DNS is the red line, and the experiments are the black and red symbols at different axial locations, 2.5 millimeters up to 10 millimeters downstream of the inlet. And so we get reasonably good agreement of the streamwise velocities for this reacting case. And then the bottom panel on the right shows the OH peak is correctly captured in the shear layer as well. So this is just a preliminary result because it's not fully refined yet, but you can see the OH movie on the left with the velocity magnitude in the grayscales as a background. And let's see if I can play it again. And so you can see the flame is anchored on the bluff body, and OH, or the OH kind of demarcates the burnt product regions. If we look at the fuel, or what's ammonia here in this bottom right is fully consumed where you have OH, but you still have a lot of hydrogen left, even at the base, which might help assist with anchoring that flame, even though the ammonia is consumed. And then you see a lot of hydrogen also going downstream. This is only 2 levels of refinement. We need to go to 4 in order to be fully resolved. But this is our initial preliminary simulations of this. We went to a much simpler geometry after this, which is this inverted diffusion flame. And so again, first stage is fuel-rich ammonia air flame. And the second stage injection is air injection is to burn off the remaining hydrogen. And we derived our run parameters in the simpler case from the Hegseth burner and LES that was presented last year at ASME Turbo Expo. So NOx here depends, of course, on the second stage combustion, mixing, and residence times. And so we're going to use DNS to try to figure out what's going on. In this configuration, a secondary combustion zone, the sketch of the configuration is shown in the upper right corner. And as I said, by DNS standards, this is the first time that an inverted turbulent diffusion flame has been performed. And this configuration consists of 4 oxidant air transverse jets that issue into a cross stream of highly diluted excess fuel and products from a hypothetical first stage primary combustor that's not represented in our setup. And all cases feature a cross flow of hot equilibrium products of rich ammonia, hydrogen, nitrogen air flames where 10% by volume of the ammonia is cracked to form hydrogen, nitrogen, and then you see 4 jets and cross flow of dilution air. Here we preheated the air stream to 780 Kelvin, and the physical extent of the domain is about 8 times the slot jet height, and where the slot jet height is 3.6 centimeters. And we ran 4 different cases to investigate the air split ratio. 3 cases at different equivalence ratios. And we also looked at in the 4th case, the impact of ammonia slip of about 4% on the combustion process that takes place in this secondary combustion zone. All of these cases were run at a realistic gas turbine pressure of 25 bar. And the equivalence ratio for the hot cross flow for all 3 cases was set to 1, 1.1, 1.2, and 1.3, which is where Kobayashi and others found that the NOx emissions to be minimum. So the ammonia slip case was done only at the 1.3 equivalence ratio. All of the cases have the same overall fuel and air mass flows, so that the averaged outlet temperature of the combustor is 1900 Kelvin. And so in this manner, then all of the cases have the same firing power, that we can make a consistent comparison across all of the different equivalence ratio cases. The global equivalence ratio for all these cases was 0.55. And the fourth case with ammonia slip has the same overall global stoichiometry and outlet temperature, but close to the wall, the hot product stream from the equilibrium products was replaced with a mix of ammonia, water, and nitrogen at 780 Kelvin. And then the velocities are density adjusted so that the mass flow rate is constant across the inflow plane, and the temperature of the cross flow for that ammonia slip case was increased by 336 Kelvin to compensate for the heat loss caused by this ammonia slip flow. And let's see. And so these thermochemical parameters I just described represent an actual RQL combustor condition, or close to one. Okay, so the turbulent air jet Reynolds number, I should say, also is about 20,000. And again, we use the 19 species mechanism. So here I'm showing the temperature isocontours with the air jets mixing with the homogeneous hot crossflow, which leads to heat release occurring in this thin layer on the windward side of the air jets, so upstream of where the air is injected, as well as in the downstream regions where air mixes with the hot crossflow stream. And then for the case with ammonia slip, the crossflow, as I said, is at a slightly higher temperature to get the same outlet temperatures for the other cases. And the cold ammonia and products are transported then along the boundary layer near the walls, which leads to a more complicated burning pattern as the air jets mix with the cold ammonia, mixed with products, and with the hot central cross stream containing both products and hydrogen. But in both cases, the peak temperature downstream of the air injection appear to be pretty similar. And we also see pockets of high temperature regions that persist farther downstream towards the outlet. And so you can see that clearly in the image. You can see those little pockets that are bright yellow near the wall as you go downstream. The movie here is just showing an animation of the OH radical from these 4 inverted diffusion flames as it moves downstream. Okay, so then if we look at the statistics, this is a slide that contains the corresponding PDFs of the temperature for the 3 equivalence ratios and for the fourth case, which has got rich ammonia slip conditions. And this is a PDF temperature conditional on the mixture fraction. Also in the gray line represents the conditional means. And for cases without ammonia slip, from 1.1 to 1.3 equivalence ratio, we see a relatively small differences in temperature for a given mixture fraction, with the biggest variation being close to the stoichiometric mixture fraction, which is denoted by the gray vertical line on the right. The lighter gray dotted line represents the global equivalence ratio of 0.55. So at the higher temperature, and then for case D, what we see is a very large, the case with ammonia slip, we see a very large temperature variation in the cross stream, and this is due to the cold ammonia slip as well as in the flame zone around the stoichiometric region. So that's the largest variance in the temperature. Okay. So then if we look at just a slice through this inverted diffusion flame, we see that all three cases, 1.1, 1.2, behave similar to the phi of 1.3 case, with the exception of slightly higher inlet temperatures, but lower heat release rate for the rich case, or lower heat release rate as the cross stream becomes leaner. So phi of 1.1 has a lower heat release rate compared to 1.3, which has more hydrogen, higher, and therefore higher heat release rates and temperatures. For case C, where phi of 1.3, we see that NO production starts downstream of the air injection, but we see higher concentrations of NO only farther downstream. And the high NO mass fractions that we see coincide with regions of high temperature that are these unmixed pocket-like regions that result, as I said, from incomplete mixing. Now we compare the equivalence ratio 1.3 case with the case where we had 4% ammonia slip on the bottom panel. And here we see significant differences. As I said, for phi of 1.3, NO production starts downstream of the air injection, but you only see higher concentrations of NO farther downstream. But the behavior is very different for the case with ammonia slip, where there's a lot of NO formed just downstream of the air injections in regions of very fast mixing. That's because, as I said before, the HNO pathway when you, for ammonia or fuel-bound nitrogen, that HNO mechanism is super fast, and so it can withstand very high mixing rates that you see just downstream of the air injection. The peak values that we get in this immediate region behind the jet, the air jet, doesn't go up any further as you go downstream. However, the downstream regions that have high NO mass fractions appear to be larger than for the phi of 1.3 case without ammonia slip. And so there's more NO being produced overall when you have that tiny bit of ammonia slip. And although I'm not showing it here, the 1.1 and 1.2 cases look similar to the 1.3 case. So what does this mean overall if you integrate all the NO to get a global NO emissions picture? So this plot on the left plots the normalized NO, normalized by the equilibrium value, versus streamwise downstream position. And I plotted all four cases, 1.1 through 1.3. And then the fourth case is the 1.3, including a little bit of ammonia slip. And so if you look at this image, you see that the amount of NO that's produced at the outlet depends on what comes in at the inlet, the amount of NO that comes in at the inlet, and then what's produced in the post-air injection region. So it's a combination of those two effects. Notably, if you have a richer first stage combustion, let's say 1.3 compared to 1.1, you would have a lower inlet NO, you have less oxidant, but you have, as a result of the increased amount of hydrogen that comes through, and higher temperature and higher heat release rate, you generate NO production faster in the second stage. And then what you can see, so you can see that the rise rate of NO is much faster post-air injection for these the richer the fuel, the richer the equivalence ratio is. But notably, what we see is that the ammonia slip gives you much more significant, faster NO production. That's that gray line that increases rapidly just immediately downstream of the air injection. As I said, it's because HNO pathway for producing N2O is super fast, and highest scalar dissipation rates and mixing rates occur right after that injection. And then it remains high overall up to the exit plane. But despite all of this, we find that the normalized NO, normalized with respect to the equilibrium value, is only about 20% of the equilibrium value. So that's a significant reduction in NO due to this RQL configuration. And then I've drawn two dashed lines here that corresponds to perfect mixing, like in a reactor. So if you could somehow improve the mixing characteristics even more, so you don't get those little pockets of increased residence time where thermal NO loves to, downstream where the thermal NO loves to grow, then you could get the NO, normalized NO down as far as under 10%. So there's some headway there to go from 10%, another 10, 15% reduction if you can figure out how to mix this thing better in the second stage. Okay, so as before, we looked at the NO formation pathways. So this figure shows the normalized integrated rates of progress for the individual reactions that involve NO. It shows the major pathways that NO is produced for the different equivalence ratio cases and for the case with slip, ammonia slip. So without ammonia slip, I'll just say the thermal pathways are the predominant production pathway since there's no ammonia left in the cross-flow mixture. Different to the behavior of the turbulent ammonia hydrogen nitrogen air flames that I showed before with just one stage. And we see that the main pathway for production of NO is through the reaction N2 plus O atom forming N plus NO. That's the largest contributor to NO production. And that's followed by N plus OH forming H plus NO, and then N reacting with the air, O2, forming NO plus O. And consistent with the global means that I just showed you, the richest case features the largest thermal and hence overall NO production rate, followed by the leaner cases 1.2 and 1.1. And so again, since the thermal NO pathway is highly sensitive to temperature, the higher the equivalence ratio in the cross stream gives you a higher temperature peaks downstream in the air injection. And so that's why you get that higher thermal NO for richer flames. The picture's a little different when you have ammonia slip because the NO production is dominated then by the HNO pathway, as I've already said, and that's predominantly the reaction HNO plus a third body forming H atom plus NO. And that leads to production of NO from the fuel-bound nitrogen. We also see a slight shift in the thermal pathway when we have ammonia slip with a reduced contribution from the pathway of N2 plus O goes to N plus NO, and increased contributions from the N plus OH pathway. And in addition, we see that there's additional, the reactions responsible for the DNOx pathway also contribute to the production of N2O. So it's useful to see from these diagrams exactly where your NO and N2O is produced. So the next topic was then, what does mixing do to, what's the influence of mixing on the NO formation dependence? And as I've already alluded to, that higher, and what I'm plotting here is the scalar dissipation rate in the top panel, and then in the bottom panel are bins of scalar dissipation rate based on different quartiles of dissipation rate PDF. So it's kind of like a cumulative distribution function, if you will, conditioned on mixture fraction to look at different regions of mixing in the jet. And so you can see the highest mixing rates occur on the windward side of the air injector and then immediately downstream of the air injection system. And that's shown by the deep red colored highest quartile of mixing rates shown in the bottom plot. So if we look at it statistically, and we condition the integral of the NO net production rates conditioned on the mixture fraction, Z, and further conditioned on the binned CDFs of scalar dissipation rate in several different PDF quartiles, which I just showed you in physical space, then you can see that for all cases we get more NO produced in higher mixing rate regions. So as you go from the dark solid lines to the dashed dot lines, you get more NO from the equivalence ratio 1.1 to 1.2 to 1.3, and including ammonia slip. But you see that most of that NO is produced between the stoichiometric mixture fraction and the global mixture fraction of 0.55. That's the region where NO is being generated. And we see also that as the cross-stream equivalence ratio goes up, so does the amount of NO that's being produced in regions of more intense mixing. So as you go richer, you get more NO there. And the case with ammonia slip, the bottom right panel shows a lot larger fraction of NO that's produced in the highest quartile of scalar dissipation rate. And again, this is due to the fast combustion process involving HNO, production of nitrous oxide, when you have fuel-bound nitrogen with the ammonia. So that's the upshot of this. So when we conclude this section, I want to say that we found that increase in pressure amplifies a lot these thermal diffusive instabilities for lean premixed flames in the presence of hydrogen. And we've seen this theme throughout these lectures, is that a little bit of hydrogen goes a long ways, whether it's pure hydrogen, whether it's mixed with syngas, with methane, or with ammonia. The personality of the flames is predominantly controlled by, a lot of it's controlled by hydrogen, and that effect is amplified when you move up in pressure. We found that the latest bluff body flame simulations show reasonably good, promising results in terms of using AMR to simulate flames with more complicated geometries. And the rich quench lean DNS at high pressure show that NO emissions reduction a lot. You only get about substantially less than equilibrium conditions, but also it shows the very detrimental impact of ammonia slip. So you want to avoid ammonia slip at all costs, because that really bumps up your NO. And so let's stop here and maybe take a quick break.